Okay, hello and welcome everyone. I'm Peter Robinson and this is the Ethereum Engineering Group Meetup. And today I'm presenting, as is Zhenyang and Angela. And so we're going to talk about the creating cross-chain applications using a technology called the Crosschain Protocol Stack and GPACT. And so a lot of people know me already. So I don't know, I'm a technical director at Consensus. But Angela, why don't you go ahead and introduce yourself?
Hi, everyone. I'm Angela Potter. I'm a product manager at Consensus, working on cross-chain protocols, so working really closely with Peter and Zhenyang. And I've been at Consensus for about 6 months, and I'm based in San Francisco. Zhenyang, you want to introduce yourself?
Sure. Hi, I'm Zhenyang. I've been working Consensus in protocol teams for a bit over 4.5 years. So I've been involved in all sorts of Ethereum projects, a little bit on IPFS and Filecoin, and yeah, cross-chain transactions. So that's me. Back to Peter.
Thank you. All right. So normally I ask other people to share their slides, but this time it's going to be me, and I'm going to get the slides into presenter view and do that trick with Zoom where the last thing your last action is on the screen that you want to share, so it's easy to find. And there are my slides, which hopefully everyone can see. Yep, I can see some nodding. Fantastic. Okay, so cross-chain applications using the Crosschain Protocol Stack and GPACT. And there is a massive agenda, but don't be daunted. We'll work through it. So the Crosschain Protocol Stack, it's this idea that for cross-chain applications, you really need 3 layers of a stack. You need to have an application layer, which is where software developers develop their applications. And then you have a function call layer, which allows you to do function calls across chains. So you could have a call execution tree, which calls from one chain to a contract on another chain. So that function call layer manages that. And then you've got the messaging layer, which is all about proving that something has happened on a remote chain. And that allows the higher layers to operate. And GPACT is a protocol which operates at that function call layer. So what does GPACT give you? Why would you be interested in using GPACT? So one of the core things that it gives you is atomicity. So you either have updates are updated on all of the chains, or they're discarded on all of the chains. So it allows you to ensure that you've got a consistent state across chains. And why that's important, so imagine you had an application like this, where you've got an application, application contract on one chain calling an application contract on another chain. So if you've got a revert there that could happen, and you've got a whole lot of logic. And so you can imagine that if that transaction does fail, then you're going to have an inconsistent state because you'll have done something on the source chain, but not on the target chain. And so you can imagine, say, Alice, she wants to transfer 2 ETH to the destination chain. So she might escrow 2 ETH and hoping that 2 ETH will be generated on the target chain. But if that doesn't happen, then you've got this inconsistent state problem, and invariably bridges fix it by having an admin go in and say, roll back the transaction and give Alice her 2 ETH back, or maybe do something on the target chain. And having some centralized admin in what's supposed to be a decentralized cross-chain protocol is a pretty scary thing. So yeah, it's not good. Another thing that GPACT gives you is multi-chain. So most of these protocols only work across 2 chains, whereas GPACT lets you have a call execution tree that goes across many chains all at once. You can get return values back and act on them. So say this trans in cond and destination blockchain, it can return a value, and then the code there on the source chain can actually act on it as it's happening. As well, you could have conditional logic. So you could be calling something in blockchain 1, but then maybe you call something in blockchain 2, depending on some conditional value. And so you're not locked into some call execution tree and you don't have any flexibility. So it allows for that level of flexibility. It also allows for application authentication. So you might, in normal Solidity programming, you typically have something like require message sender equals some authorized address. And so it gives you a similar capability. So is the call that's coming in, is it coming from a source blockchain and a source contract that I'm happy with? And do I trust it? And developer experience is something that we've worked really hard at, and I think we've done a pretty good job at. So with GPACT, you're getting a similar sort of experience to what you're getting with Solidity and the EVM. So the function calls are across contracts or across blockchains. So it's not just inter-contract calls, but inter-contract calls across other blockchains. And as well, so this allows you to do composable programming. So you could imagine you've got a bit of functionality in a contract here, a bit of functionality in a contract there, and you can sew these pieces together. You can compose them into an overall application. And from the actual contracts perspective, it's a synchronous execution model. So even though the overall is asynchronous, from the actual Solidity code, when it asks for a value, does a function call, it gets that value immediately. So how does GPACT work? So it's a protocol which there are some IEEE peer-reviewed papers that have been published about it, but that one, there's a link as an open access paper. There's also an open source GitHub repo that you can use. And so the idea of the protocol is you have your call execution tree that you work out. So these are the entry point functions on the entry point contracts on each blockchain. And you work out what the expected values are. So you know what values you're going to pass into the source contract, the root contract, but then from there you need to simulate to work out what these other values are that you're going to have. And so then what you do is you have a start call, and in that start call, which is essentially a function call into a contract on the source chain, you say, this is the call execution tree I plan to execute. And then that'll publish events or emit an event. And that event is used in segment calls to say, well, I'm executing this part of the call execution tree that we were going to execute. And you'll run that part of the program that needs to be run on that chain, and it will return a value. And then that return value, or whether it failed, maybe the whole thing failed and it reverted, is fed into a segment event. And then you go from the leaves of the tree, call execution tree, up to the root. And eventually segment after segment make it to the top. And then you execute the root. And so if all the segments have executed okay, and it executes okay itself, then it will emit a root event saying, hey, let's commit all the changes. Otherwise, it'll say, hey, let's discard all the changes. And then finally, there is signaling events as well that happen, and they commit the changes on those other chains. So there's a few things to consider. There's a timeout that happens as well that's registered when you do start. And so if things take too long, then the whole transaction expires and everything is discarded. As well, I've said that, we published that call execution tree in the start event. So that's how things happened with GPACT v1. In GPACT v2, which we're in the middle of putting together, it is going to do some privacy preserving features. So even if that chain that you're working on is, say, really a ZK rollup or a consortium chain, or maybe another chain where you don't want to publish the information, then that will preserve that privacy. And that's also quite useful if you're in a situation where there might be front-running attacks, which I guess is pretty much the whole blockchain ecosystem. And so that'll help in those scenarios too. So from a code perspective, how this all works is you have some infrastructure contracts. So the cross-chain control contract, and you've got a messaging layer contract as well. And so the idea is that you have these function calls in this cross-chain control contract, say start, segment, root, or signaling for those various functions that need to execute. And the first thing it'll do is it'll say, well, for the events that have been wrapped up in this function call, are they true? Did they really come from that source chain that you've said they did? And you'll verify that information is correct. So the verification algorithm depends on the source chain, and you can have one different verifying mechanism for each source chain. And then assuming that that goes well, then you'll call the business logic at the application entry point. And then maybe it has some storage update that it needs to do. So it updates some storage slots, in which case it'll indicate that it's got some locked storage to the cross-chain control contract. And equally, it'll also could call out to other business logic contracts. You could also do a cross-chain function call. And in that case, it says, hey, I have been asked to do this cross-chain function call. Does the call graph indicate that this should happen? And if it does, then it's all good. Otherwise, it'll fail. And with that number 6 there, the cross-chain function call, it'll provide the parameters of the function call as well. And if they don't match, again, things will fail. So the messaging layer in this whole system relies on an overall set of contracts, and they've been standardized in the EEA, so the Enterprise Ethereum Alliance. And so we're still working on the mechanism for a variety of different messaging layer mechanisms, but all of the mechanisms will fit under this API, which is essentially a Solidity API saying, if you write a verifier that conforms to this API, then any function call layer can use your verifier for your source chain. And importantly, with those messaging layer functions, is that they can only act on events that have been finalized. So as we know with, say, proof of work, you've got probabilistic finality, and say some proof of authority chains have got instant finality. Ethereum 2 with proof of stake, we're going to have a varied finality. And please have a look at the talk from 2 weeks ago where Mikhail talks through in detail what finality means in Ethereum 2. So the architecture of the system. So I've talked a lot at sort of a very high level, but now let's actually walk through how the actual system fits together. So you've got 3 blockchains here, and you have a set of relayers, or testers. So those relayers or testers, they really are solidly linked to a certain blockchain. So they could represent more than one blockchain, but at the end of the day, they're attesting to an event happening on a source blockchain. On that source blockchain, you've got the application contracts and the Crosschain Protocol Stack contracts, and they're on each chain. Then the application is going to have an SDK that integrated into it to help it use and operate the GPACT protocol. And so that SDK is going to talk to all the blockchains and as well maybe a message store. So the actual mechanics and interaction with the relay or attester depends on the verification mechanism for that chain. And so those relay attesters, depending on, again, the protocol, they will read events, and maybe they might even write signed events or write root values to the blockchains. And so the SDK we're working on, we've got TypeScript and Java. So within that relayer, the idea is that we have a message observer. So it observes events happening from a certain chain, and you can have multiple message observers observing different blockchains, and they can have different finality requirements as well, because maybe one observer is for low value events, whereas another one might be for high value events, and you might want to only verify that something's happened if a larger amount of finality has happened because the transaction involved is, say, millions of dollars. And there's a router which routes the various messages that are going through this relayer system to the correct dispatcher. And then you've got a signer, which is the relayer signing that this that it's attesting to this thing having happened. And then the message dispatcher, it's depending on the actual system being used, it could be dispatching raw signed events, it could be dispatching signed Merkle roots or block headers, or it could be dispatching this information to a message store, which is essentially a CDN style system where you're essentially just reading information. Okay, and that slide's got yet more detail, which I think really says what I've just said. And at the moment, the main deployment option that's available to you using this system to try it out is Docker Compose Up. So we've got some Docker containers, and we've got a Docker file which will allow you to run the whole system, including 3 blockchains. And we're looking at doing a cloud deployment to make it easy for people so they don't have to deploy anything. If you're interested, please get in contact with Angela and me and Zhenyang, but Angela in particular, because she's the product manager, and say, hey, we would really like to try this out. It would be lovely to have a cloud deployment that involves, I don't know, a roll up and maybe an Ethereum testnet or something. Okay, so cross-chain application contracts in Solidity. So earlier I said that there were infrastructure contracts, and so one of them is the cross-chain control contract. And one of the things it offers is an API for you to do a cross-chain call. And so what you do is you include this cross-chain function call interface in your code, and then you can call cross-blockchain call with the blockchain ID that you're calling to, the address of the contract, and the function call data. So the function call data is going to have the function selector and then the actual parameters encoded in ABI format. And for instance, here's an example where you've got, say, the CBC contract is available to you, and you cast that as an address and then back to the function call interface, and you do cross-blockchain call, passing in the blockchain ID of, say, the hotel blockchain, the address of the hotel contract, and then the parameters and function that you actually want to call. And there's also the ability to return values. So we've got a function that returns a uint 256. And again, if you look at this, you're calling very similar mechanics, and you're getting a return value. So I said that there was authentication, which allows you to make sure you're being only called by authorized parties. And so how you do this is you make sure as a starting point that you're being called by the CBC, the cross-chain control contract. And then after that, you call a function, decode atomic auth parameters. And that's something that we've written for you that you can just inherit. And then it's a matter of making sure that the root blockchain and the source contract and the source chain actually match something that's authorized. Another area is lockable storage. So the lockable storage mechanisms are actually programmable. And so you can write your own, or you can use what we've written. And so the big reason for that is that the lockable locking mechanism is really going to come down to, is going to be application specific. And so, do you do lock on read, or do you just do lock on write? Do you lock the whole contract or just a single storage location? So these things give you different security properties, but they also give you different gas cost properties. And so we've put that into the hands of you, the user. The default is that it's locking per storage location and lock on write, which is good for most situations. So, and I think I've just said, that slide says what I've just said. Okay, and there are, so we've got the default implementation has a ton of functions. And so the idea is that you have a key, and a value that you're storing. And so this works actually very much how Solidity uses the EVM to store information. And yep, here we go. And so you can imagine that, yeah, all right, so I don't have a slide on this. Yeah, so you can imagine you have, say, you define your storage slots as, say, that key value. So that could be 0, 1, 2, 3. And then you, that then defines which locations will be used. So you can see that with the, say, get uint 256, there's the basic one, committed and provisional. And so the basic one will revert if a storage location is locked. The committed one will just tell you the value that has been committed previously. And so if there's an active cross-chain call, it won't tell you about that. And then provisional will tell you, well, here's the provisional value that's in process. And why you need to be able to know about committed and provisional is, you could imagine, say, you've got a contract which is about value transfer, and you want to know, well, what's the minimum balance this user has based on the outstanding transactions, or what's the maximum balance they have based on the outstanding transactions. And so you need these committed and provisional. And so we've got an example ERC20 contract. And if you look at that, that shows how to use those functions. Oh, all right. Now this is where I'm showing the example of how you use a storage slot, essentially. All right, and as well, we've got array processing functions. And again, it's a matter of defining the storage slot and the array index. And we've got maps, which is, again, about defining the storage slot that you're going to use, and then defining the map key and the map value. So it's rather than having, say, some nice syntactic sugar, you're going to have to use a function call. And we have double maps and triple maps as well. Okay, over to Zhenyang to talk about the JavaScript library.
Cool, thanks, Peter. So I'll briefly talk about JavaScript library. We have got a self-contained truffle project that can be used as a skeleton to build any GPACT application. It has an example Solidity contract that will be deployed on-chain, and also a JavaScript dApp to interact with the contract. Next slide, please. Cool. So on the contract directory, you will find the Solidity code for the example contract, and also a folder storing all the dependencies you will possibly need. So at the moment, GPACT is sort of like alpha beta version. We haven't done any official release yet. So currently, this is how you can access the GPACT Solidity library. Next slide, please. So this is what the example contract looks like. You can use the default general purpose log post storage contract Peter mentioned earlier. If you don't, then the GPACT application must implement the log post storage interface, so that during the middle of a cross-chain call, you can lock the contract or part of the contract and have provisional updates. Later, when we finalize a cross-chain call, GPACT will be able to send signals to the contracts to either commit or to discard the changes. Atomic hidden auth parameters is a utility that you can use to verify incoming cross-chain transactions, especially when your application needs to know and to verify who makes that cross-chain call. Also, every GPACT application will, of course, need to store the GPACT contract on that particular chain in order to make cross-chain calls or to handle cross-chain calls. Next slide, please. We have an example dApp. Under the app directory, it is written in JavaScript. You can use app.js to sort of like access the example contract methods or to make cross-chain calls. There is also an SDK folder where you will find all the libraries or the SDKs you will need to write a JS dApp. again, the SDK is sort of like pre-alpha, so we haven't done a release yet, but everything you possibly need is here. Next slide, please. So for example, in the dApp, you will need to have a chain manager that is used to store and manage access to different chains. You will also need to have a message store manager that is used to request event proofs from relayers. And simulator is used to simulate a cross-chain function call and build a call execution tree. The call execution tree will then be used by the executor to execute a cross-chain transaction. Next slide, please. So the local environmental setup is fully automated. You can easily use Docker to spin up and configure the 3 local chains and relayers, so you don't need to worry too much on the messaging layer or the function call layer. Instead, you can just focus on the application layer. And I have put a lot of comments in the example application code, so it should be easy to follow, hopefully. Next slide, please. And one final thing, that the JavaScript library is sort of like under development right now, so you are likely to see some major changes on new features coming to the repo constantly. And yeah, that's all for the JavaScript library. And I'll hand over to Peter for the Java library.
Yep, sure. Thank you, Zhenyang. So the Java library. So the Java library provides you the ability to write your code in Java. Yep, it's you can. So there are a whole stack of Java examples. And so to start out, you just run Docker, so Docker compose up, and then you kick off IntelliJ, and you can just run one of the many GPACT examples. And I think we decided we wouldn't dive deep into the Java library. I think a lot of it, or similar to the TypeScript library, that's in active development, but you can certainly use it and start playing with it and giving us feedback. Okay, walking through an example, and this is you, Zhenyang, I think.
Yeah, back to me again. Okay, yeah, I'll walk through an example of a typical hotel train problem. So imagine a scenario where a travel agency wants to book a hotel and a train on behalf of a user. We need to make sure either both reservations go through or fail together. So we won't be in a situation, that you booked the hotel, but the train tickets sold out. Next slide, please. Yeah, and by the way, this train hotel example is part of the GPACT repo. So if you are interested, feel free to check it out. The train and the hotel contracts are essentially just a logball, sort of like a logball map that maps dates or seats or rooms to whoever purchased the ticket. And when we do the booking, we pay also using a logball ERC20 token. Next slide, please. The travel agency contract also has a logball storage map that stores successful booking info. On the right-hand side, you can see that we have a function named book hotel and train. And what it does is using the GPACT function call contract to make a cross-chain call. From a solidity contract point of view, to make the function call straightforward, you just need to pass the destination chain ID, the destination contract address, and the function call data to the GPACT contract, and it will make the call and return value to you. Next slide, please. However, when we develop the off-chain application, we will need a bit extra work to make that function call instead of like calling the method directly. So what we will need to do is first to use the SDK to run the simulation and build a call execution tree. And then we use the SDK again to execute the call execution tree in a reverse order. So in this way, every cross-chain call returns immediately from the contract perspective, as we have already executed the cross-chain calls earlier and obtained the return result. Next slide, please. So this diagram shows in detail the whole actual process involved when we execute the execution tree. In short, we submit a start transaction to indicate the start of a cross-chain call. We then execute the segment transactions from the leaf nodes in the executing tree all the way to the top, and the contracts involved will be locked until we finished executing the roof node in the execution tree and send signals to unlock those contracts. So cool. That's it. Anyway, again, as mentioned, this example is part of the GPACT repo. So if you are interested, feel free to make a fork and play around with it. And there are many more different examples too. So cool. I'll hand over to Angela.
Yeah. So I am a product manager, so I don't have any technical diagrams, but wanted to run through a few really high-level use cases as inspiration for the type of thing that GPACT can enable. So I'll start with a simple one, which is a cross-chain NFT purchase. Say Alice wants to buy Bob's NFT, but Bob's NFT is on the Palm network, and Alice doesn't have any funds on the Palm network. She only has funds on Ethereum. She should be able to buy Bob's NFT on a different network in a single atomic transaction and ensure that when the NFT is transferred, the payment is going to be transferred as well. Next slide. So that's kind of a simple version of a cross-chain NFT purchase, but we can imagine this extending this a little bit further. Perhaps Bob has several NFTs for a blockchain-based game, and these NFTs actually span across multiple blockchains. This example is really a variation on the hotel train example that Zhenyang just went through. But there's actually a blockchain game called Galaxy Fight Club where you have a character on Ethereum mainnet, and then you have gear for your character that's issued as NFTs on Polygon. And so imagine that you have a character and a set of gear and want to be able to sell those as a bundle, where you're setting a price for the whole group and want to be able to sell them all at once. GPACT would enable you to do that and be able to take payment on either blockchain, sell your NFTs on multiple blockchains as one set. Next slide. Another interesting example of something you might want to do with NFTs using GPACT is being able to do an airdrop for NFT collectors on a different chain with some sort of complex logic. We see this a lot in the NFT space, where if you own one NFT, you might be eligible for some reward. If you own an NFT at a specific time, you might be eligible for some reward. But what if you want to give a reward to your NFT holders on a different blockchain, and you want it to be more dynamic than just a single airdrop? Maybe you want to give a reward to people who've held your NFT for 30 days, and you want to be able to drop that reward to them once that time has been hit. You could, and you want that reward to happen on a different blockchain because you don't want to pay for gas on mainnet. This is another type of use case, a complex airdrop mechanic that GPACT would enable. Next slide. DAO voting is another interesting area for some complex cross-chain applications. A lot of DAOs will issue governance tokens for their DAO on Ethereum mainnet. So if I own some amount of governance tokens for this DAO, I can vote in DAO proposals with those tokens based on how many I have. But if I want to vote on chain, if the DAO implements on-chain voting, it's going to be pretty expensive for me to, as an individual, vote on every single proposal. So often what happens is users end up delegating their votes to somebody else who can afford to pay the gas fees, which makes it maybe not as decentralized as the DAO had hoped. So wouldn't it be great if I could hold governance tokens on Ethereum mainnet, but be able to actually submit my vote for a DAO proposal on any blockchain that has lower gas fees. Maybe I want to be able to vote on Avalanche. Maybe I want to be able to vote on Polygon. We should be able to track that across any number of blockchains. Next slide. And I think this is the last example that I'll go through quickly, which is bond residuals. I think there's actually probably a bunch of different potential use cases around bond residuals, but one example is that say somebody owns a bond which pays them some sort of royalties or residuals on like weekly, every Monday at 9 a.m. And they need to be able to receive residuals on a different chain than they actually own the bond. As that bond transfers ownership, the payment blockchain needs to be able to track who actually owns the bond at that other chain and pay the correct residuals accordingly. And so with GPACT, you could enable something like this. You could also imagine that you actually want to be able to transfer the bond across different blockchains and be able to validate ownership of that bond and continue to pay residuals to the right person. So I think that's the last example. But yeah, I just want to emphasize that we're really just kind of scratching the surface of potential use cases. It's still very early. So if you have things that you're trying to accomplish, other types of cross-chain applications, we would definitely love to hear them and figure out if there's a way that they can be enabled with something like GPACT.
Thank you, Angela. Okay, so let's see if I can flick to the next slide. Yeah, all right. So before we hit questions, let's go through some final thoughts, which is that, look, the GPACT and the Crosschain Protocol Stack are they're still being developed. And so you could imagine that when you're using it, some stuff may not work completely well, but I think it is game-changing technology, and I'll address Lecky's question, and I'll also see if Zhenyang and Angela want to talk to it as well. But I think relative to the existing tech, it is quite game-changing, so we've been working really hard on this, and I think it's it'll be something that's good to work with people on if people are interested in contributing to the open source. All right, so Lecky put it out there and said, why reinvent the wheel now? How does it compare to Chainlink and other protocols that have been in production, been production proven for a long time? So, good question. So Chainlink in particular is an Oracle-based technology, and it is an Oracle-based technology where the idea is that you have some people who say, look, this thing's happened off chain, and then you then put it on chain, and then you can say, right, that's happened on chain. So that's the basic idea. And the idea is that you're supposed to be able to review the code that's happening off chain to be happy that it's really going to give you the results that you're hoping for. And Chainlink publicized a cross-chain interoperability standard, so which was actually the same name as the EEA were using for their cross-chain interoperability standard. So there you go. I guess lots of very similar names in the cross-chain space. So Chainlink offers essentially what you could see as think of as a messaging protocol. And so it allows you to say this thing's happened on a chain, but say if something bad happens on that target chain, then it and all of the other protocols are not going to be able to unravel that for you. They're not going to be at the protocol level able to do the atomicity, whereas the other protocols generally, require someone to jump in as an administrator to unpick that. And it also isn't going to allow you to have that more complex business logic communicating a business logic on multiple other chains. So I've said a few answers there, but Angela, what are you thinking?
Yeah, I think that's right. I mean, I think the protocols that are out there, I mean, there's a bunch of, I think, different versions of like cross-chain trilemmas. But I think the protocols that are out there, there's a lot of really generalized protocols that might allow you to do something more complicated across chains, but generally they're not going to be atomic in the same way that GPACT is. So they don't allow you to have that assurance that everything will either succeed together or fail together. So specifically in situations where, yeah, you might be wanting to pay for things across multiple blockchains, you need to be able to have like all of these different pieces locked in and make sure they're locked in before you execute the whole thing. And so I think that's kind of what like a big value prop that GPACT brings to the table. And then I think you also have protocols that are atomic, but they're very like use case specific. So like hash time lock contracts allow you to execute atomic swaps, but it really has to be that very kind of simple like person versus person trade of assets. And if you want to introduce anything more complex, or you need to introduce something from another blockchain, you're not going to be able to do that with that protocol. So having that combination of atomicity and generalizability, I think is kind of the value prop that GPACT brings that we don't see in any of the other protocols that are out there in production today.
Could you explain a bit more about the atomic that if a transaction in chain A and then a transaction in chain B fail, it would fail the transaction in chain A? Is that what that means?
Yes, essentially. So what you do is you, so you're going to do so if you think about it, you do the start, which happens on chain A, which says the call execution tree. Then on chain B, you would execute that segment of the function call, and say it reverted, then that would mean that that segment failed. And then you would execute the root transaction on the source contract, and it would say, all right, the overall thing's failed. So let's send out, I mean, we can now do a root event saying the whole thing's failed. So yeah. So yeah, so in answer to your question, yes, the locking and the overall protocol means that even if you've got chain A, B, and C, if the thing on C passes, the thing on B fails, then you can then make sure that the thing on C rolls back. And so, overall, everything is stays in sync.
I see. Interesting. I think it's not a real atomic. It's a hack around of atomic, because I have back to you also mentioned you want more use case. So for example, I have a use case that really need Atomic is I'm trying to get the data cross from the beacon chain. I want the validator balance from the beacon chain, then fitting it through the beacon chain API and fitting that back to the L1. But I need that to calculate the reward on the real time, but which is not really, it has to be Atomic. For example, I need to calculate the reward, say there's a 35 EVA and compare before was a 32 EVA, and that is 3 EVA with reward on the beacon chain, and then I need to mean 3 EVA, but it's not really possible for real Atomic as it is a different chain and there's a delay to get the data and then fitting it back. So the user cannot get claim in one transaction. But I think your one is, it will be still be 2 transactions. For example, your first transaction still go through, but like locked it, but then you will have a second transaction to change the lockable one. So it's still like 2 transactions, but it looks like a reward, like it will be still 2 transactions, but not a real Atomic, I think, yeah.
Yeah, so it's not, it's not magically doing one transaction that arcs over multiple chains. So that's correct. But, and it does require, as I showed, say two transactions on the target chain and 2 transactions on the source chain. But at an overall meta level, so, you know, if you look at the meta level, it is atomic because you're either, or everything's going through or everything's being discarded. But going to your particular use case, so you're on the beacon chain, and so is this the beacon chain once you've had the execution chain merged with it, so you're able to see the rewards there, or is this looking at the beacon chain by itself and not with Ethereum execution chain?
So it's even before merge or after merge, it still be 2 chain, the consensus layer chain and the execution layer chain. It just, they are talking through each other through the port, through the network connection. So I'm using Chainlink to through the beacon chain API to fitting the validator balance back to L1. So yeah, so that's why I'm using Chainlink, and I think that it has a single point failure that I was trying to resolve, but yeah, currently it is working. That I'm feeding the data from the beacon chain through the beacon chain API and feeding through the Chainlink external adapter, running our own Chainlink node, and then feeding the data back to L1. But it is a 2-step process that we need to have the clone job to keep feeding the data from the beacon chain back to the L1 Oracle, and then so that user can claim and calculate the reward from there, which is not real time. It will still be behind, like it can never get the latest. Like one approach is like 6 minutes. Unless my cron job is like within this 6 minutes, then it will be no latency. But it will, if we, but that's a L1, it will be a huge cost. So it will not be a real time atomic thing. But yeah, that's my use case.
Okay, all right. Well, yeah, so GPACT works between so Ethereum contracts, and I think the use case you've got is essentially going outside of the EVM to do a web call, which yeah, it doesn't handle. So yeah. So Ron, let's just make sure. Yep. All right. So Ron van der Maiden said, what underlies this by way of formal semantics? Have you looked at connections to the Lynch nested transactions area? So I can say the answer to that one is no. No, we have not looked at Lynch nested transactions, and we have not formally analyzed the protocol. There has been talk of doing it, but we have not got to that yet. And then another use case might be long transactions on a single chain that need user input. These need to be fragmented across functions in Solidity. Ron, can you expand on that? Because I'm not sure I'm fully getting that from the words you've written.
Yeah, so if I've got some sort of some functionality that is sort of a sequence of events that I want to happen in some particular order, but that requires user input. Okay. Now that obviously can't. I mean, I can do the first part of the computation up to the point where it gets to say, okay, now I need to hear from the user some input value. Okay, at that point, I've got to stop the transaction, wait for the user to post a transaction that provides that input, right? And then I can go on with whatever my process is. Right. I mean, so at the moment, the way that you would program that in Solidity is you would write a bunch of functions, and there's some state variable that says where am I up to in that longer running activity. Right. But it's a sort of inconvenient way to have to program this, and it seems to me what you're doing could also be applied for those sorts of purposes in the way that you're writing. I mean, writing code that looks like Solidity code, but actually it needs to wait for events that are happening somewhere else, that are not happening in a single transaction.
Yeah, okay. That's an interesting one and something for us to think through. I mean, at the moment, GPACT doesn't handle that sort of thing, but it's an interesting thing to ponder over. So you had another one. Also interested to see how you write the finality checks. What happens if such a check reports finality, but there is a reorg? Good question. So how the finality checking is done at the relayer level, and so it has to tell you what's final. And so the idea is that you've got to have the depth that you feel is not going to have a reorg. And you'll find that all of the cross-chain protocols rely on information being final, because otherwise you end up reacting off something that then may no longer exist. And so if you do end up reacting off stuff that's not final, then you're in trouble. So it's a matter of knowing the finality rules of the source chain. And given you're the relayer, you should know that. And then Chi Chuyan Ang said, I think the beacon chain one really relies on the protocol level thing, which sounds different to me from GPACT's use case. All right, and yes, that's what we agree. All right, are there any other questions before I start talking about the few forthcoming talks? Okay. Yeah, so that's all the socials stuff. So this is, if you want to join the actual meetup, there's the link, or you can watch us on YouTube. There's a Slack workspace. If you've got questions or you want to engage, please go there. If you want to get involved in the formal methods reading group, then please go to that Slack workspace and go to the FM reading group channel. So in 2 weeks' time, we've got Adrian Sutton, who's going to talk about checkpoint sync, and that's a syncing protocol used in beacon chain clients. We've got a week after that, Weijia Zhang is going to talk about cross-chain asset transfer and NFTs. And so he's done a lot of thinking about the different types of NFTs and hence their cross-chain properties. So I've heard a version of this talk and I know he's revising it. So it sounds like a really interesting talk. We're going to have a winter break. And then after the winter break, We've got Vanessa, who's going to talk about MEV and Ethereum 2. So she's been doing some research into this and has some ideas on how MEV is going to work in the ETH2 era. And then Ermias has got a talk together on what atomicity means in cross-chain transactions and some deeper thinking on it. So we've got a few tentative talks that are in the midst of coming together. One's on Truffle, one's on Solidity security, and there's a programming language that people in the intelligence group in Consensus have got, where it helps you annotate Solidity to do some proofs around whether your code is secure or not. We've also got someone from Infura. There's two other talks that I'm in the midst of getting together. One is on decentralized identities, and another one is on networks of accounts and trying to work out nefarious activity based on an account ID and the accounts that they've interacted with, and I think how they've interacted. So I just heard a lightning talk just 2 days ago on that, and it sounded really interesting. And I'm sure the lady who's doing that research would love to have 30 minutes or an hour to tell us more about that. So anyway, thank you again, Zhenyang and Angela, for being co-speakers today. So thank you. And look, everyone, have a great evening, night, or morning, wherever you live in the world, and have a great day. Thank you. Bye-bye.
Thank you.
Thank you.
Thank you. Bye.
Bye-bye now.
Bye-bye.